All right, so today we will look at conditions and loops, and some students had questions about, hey, can we use for loops and whatnot on our thing? And the answer is yes. And as far as approaching the homework, okay, don't feel like you're restricted. I'm not trying to restrict you on like what kind of functions or things you can use. So as long as it's in base R, it's use whatever is available to you, right? And if you need to look up the help on a function, that's an important thing, right? So go ahead and look up the help for a function and see like what kind of options you can use, and don't hesitate to use functions, even if we haven't necessarily covered. The only thing I don't really want you to do is like load packages outside that kind of just has some kind of prepackaged solution for whatever it is you're looking for. So let's start off with base R. But yeah, if you learned something in Stats 20 and you're like, oh yeah, I remember this. It wasn't, even if it wasn't covered yet in my class or something, you can use it, okay? Today we're covering conditions, loops, that kind of stuff. And a lot of the lecture notes are based off of stuff from our two textbooks, one being the basic programming chapter in Introduction to Scientific Programming and Simulation Using R, and the other being Chapter 5, Control Flow from Advanced R. Both of these textbooks you can read for free. For this one, you have to be connected to the UCLA network. And so right now, if you're on Wi-Fi, you are on the UCLA network. You just click it. It should open up over here. And you should see this thing that says UCLA Library, access provided by UCLA Library. If that's not the case, then you might need to clear the cookies associated with this website. Okay, and then you can just click download, or you can click read online, right? And you click download and you'll get the PDF. Or you can download individual chapters if you feel that's preferable. So your tuition money, you're paying a lot of tuition to be here, and part of that tuition goes to the library, and then the library uses that funding to, pay publishers access to their content, okay? And so the UCLA library is truly a great, excellent resource. And there's, if you want physical books, you can get access to so many physical books. And then, even very conveniently, we have access to a lot of digital content as well. So make sure you take advantage of the library. It's not just a pretty place to do studying, but get books and resources and anything you want to read. Use that, okay? And that's what we have. I generally try to find textbooks that are, free to students. In this class I was able to do so. There's one class where I couldn't find a textbook that I liked that was kind of free to students, and that's 102B. So for that class, if you get in my 102B class, I make you pay for a textbook. But other than that, I try to use freely available resources. Okay, let's talk about this: operators that produce logical values. So basically, all of our conditional statements are powered by this logical value, or in other languages we call them Boolean values, where you either have a true or a false. If this is true, then do this. If it's not, then don't do that thing, right? And so the way the computer reads the code and executes code is based on these logical values. So we need to understand what produces a true false value, how these things interact, because that's how we're going to power all of our code and our conditions. And so we have the standard logical operators. We have the or, we have the and, we have the not. We also have the exclusive or. And these are what we call vectorized logical operators, meaning if you have a vector of true, false values, then you have multiple vectors. It's going to go through the elements in X, compare them element-wise, and do your true or false values there, okay? So contrast that to the non-vectorized logical operators. And non-vectorized logical operators return only one logical value. So if you have vectors that are length longer than 1, then it's going to just look at the first elements only and do the kind of comparison. You've got the non-vectorized OR, which is the OR operator, but two of them. You have the non-vectorized AND, which is the AND operator, but two of them, okay? These things read left to right, only looking at the first element, the leftmost element here. So here we go. Here is vector X, which is true, true, false, false. Y is false, true, false, true. And so if we do the vectorized OR, it goes element-wise, and it goes true or false, the first element. And when you have a true or false, you get back true. True or true, you get back true. False or false is false, and false or true is true. Okay. With the vectorized AND, it does it element-wise. True and false is false. True and true is true. False and false is false, and false and true is false, right? So for AND, both things have to be true for it to be true. For OR, only one of those things has to be true for it to be true. With the non-vector OR, it only looks at the first element, true or false, and you get back true. For the non-vector AND, it only looks at the first element of each, and true and false returns false. So that's what we have there. All right, what happens if we do, if we have a logical vector or a logical vector and we compare it with a missing value? Okay, so this is something, for R, we can have missing logical values. So here I've got true, and then here I've got this container containing a logical value, but we don't know if what's inside here is true or false. So if I have true or missing, what is this going to be? True. It doesn't matter what's in here. We know because this is true, the result's going to be true. Okay. What about true and missing? What's the result of this going to be? This is we don't know, right? It depends on what's in here. If this is true, it's going to be true. If this is false, it's going to be false. But it's missing, so we don't know. So true and missing is going to be missing. Okay. False or missing. What do we get? We don't know the answer. And then we have false and missing. We know the answer has to be false, right? So exactly as you stated, we have true or missing is true. True and missing is missing. False or missing is missing, but false and missing is going to be false. And it's good, as you go through the slides, as you study and stuff, just kind of quiz yourself. And the ability to read code and expect what it's going to output is an important skill that you have to develop by kind of reading and doing things, right? So, while you have your computer, if there's a chunk of code and you're not quite sure, you can execute it and you can get the answer, okay? But your ability to kind of read a bunch of code and predict and understand how it's going to produce output is an important thing to be able to kind of work at a reasonable speed because you don't have to execute every single line of code in order to understand. That's going to be important. Executing every single line of code is important in your development and learning. And so use that, but it's also something you want to pay attention to so that you can start predicting how code is going to execute without necessarily having to run every single operation. All right, we've got exclusive OR. Exclusive OR basically is one thing has to be true and one thing has to be false for it to return true. If both things are true, exclusive OR actually returns false. There's like a subtle language, and most languages that use the word or, which is like every language, most of them are always kind of it's ambiguous, the usage of or, right? So I can ask you, do you like chocolate or vanilla ice cream, right? Do you like chocolate or vanilla ice cream? It's a little ambiguous, right? You could say, yeah, I like chocolate or vanilla ice cream. Either of those things are good with me, okay? Or you can say, no, I'm lactose intolerant. I don't like ice cream at all, blah, blah, blah. But that's fine, right? Okay, and that's an inclusive or. It's basically asking, is either chocolate or vanilla ice cream acceptable to you? And you can say yes or no. Or you could do, I could just ask the same question, change the intonation a little bit. Do you like chocolate or vanilla ice cream? Right? And now that becomes like a choice. I prefer chocolate ice cream. I prefer vanilla ice cream, or something like that. And the second one would be the exclusive or case, right? So exclusive or, true or false exclusive or will be true. True, true, true. True exclusive or true is false. False exclusive or false is false. False exclusive or true is true. And exclusive or combined with any kind of missing value is always going to be missing. we have the operators any and all. These are generalizations of or and, okay? So any is basically, are any of the values true? And if so, return true. All is, are all of the values true? And if so, return true. And otherwise, return false. So here I've got true, true, true. Any true is true. All true is all on you, true. Here I got V is true, true, false. Are any of these things true? Yes. Yes, so that's true. Are all of these things true? That's a no, so we get false. W is false, false, false. Are any of those true? That's not true. That's false. Okay, are any of these things, are all of them true? No, so we get false there. Here's a question. What if we combine a logical 0, a length 0 vector with, or null, with some vector values v? Okay, so we have some vector v of true, false values, okay? And we combine that with a length 0 logical vector, or a null. What is that going to output, okay? So if you have some vector v and you do any on v, that should result the same as just adding nothing to it, right? Length 0. So if I do any on logical 0 with v, that should result in the same as any on v. All on logical 0 v should produce the same result as all on v. Okay. So with that in mind, what would any on the length 0 vector return? And what would all on the length 0 vector return? So you can think about this, and I'm just going to give you the answer now, but you know, as you study, check back in a few days, or maybe you don't remember off the top of your head, but you know, see if you can reason through this, right? So any, right, if v returns true, right, if v contains true on any of these things, then this will return true, okay? But let's say v is a vector of all falses, okay? Then any on v will return false, okay? And so if logical 0 produced anything other than a false, then mixing anything other than a false with all falses is going to change the result here. So any on a logical 0 is going to return false, okay? Because here I've got true, true, true. Any on true is going to be true. And then if I mix in the false with this, that's still going to be true, right? And here I got true, true, false, and that returns true. And if I mix in a false there, it's going to return, it's still going to return true. But this one, okay, if w is false, 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 any on the w's returns false. But if this returned anything other than a false, that would change the result of this thing, right? Any on the logical 0 combined with the vector of all falses, if that returned if any on the logical 0 returned anything other than the false, this would be something different, and that would kind of break our code. So so any on the logical 0 will return false. Similar kind of logical reasoning applies to all on the length 0 vector. So all on the length 0 vector will return true. And this in of itself feels a little bit strange, but if you think about what has to happen when you combine a length 0 vector with an existing logical vector, we don't want that length 0 vector to alter the results of that logical vector. And so so when you do that, this has to return true. Otherwise, this result would be different. All right, we have comparison operators. Comparison operators allow us to kind of compare numeric values. So, you know, is 10 greater than 5, or is, you know, this operation, is the numeric result of that operation going to be greater than or less than something else? And you can say, hey, is it equal to, not equal to, less than, greater than, less than or equal to, greater than or equal to? We also have the in operator, and all of these are vectorized. You can also use these comparison operators for characters, all right? And characters basically are asking, hey, does it come before the other in the alphabet? Okay, so if you were alphabetize these things, you know, words that start with A come before words that start with B, and that's kind of what it means to be less than. Kind of a side effect of this is when you look at numbers, but in character form, the character 10 comes before the character 2. Okay, the character string 10 comes before the character 2 because And this is like basically saying the word AB comes before the word B in the alphabet, right? And that's what's going on here. Of course, numerically, if we had the number, if this was a numeric value, 10 is not going to be less than 2. But as far as alphabetizing, 1, 0 comes before 2, okay? The symbols also have a quote-unquote alphabetical order. There's no rhyme or reason to the ordering of the symbols. I don't know why it's in this order. It just is, but that's just, this was arbitrarily selected, and that's how it goes. Same, if you think about it, why is the alphabet in the order that it's in? It's completely arbitrary, right? There's no reason why the letter D should come before the letter E, but it's just, we just said it was somewhere long ago, and we've accepted it. And it's unsettling to see things not in alphabetical order. And there's been studies that are like, people with, last names A do better than people with last name Z because they often get called upon first and stuff. And so like with elections, they like change the ordering of the alphabet and then they alphabetize things in this arbitrary order and stuff. It's a little bit funny, but anyway, that's what we have. Okay, you got these is functions. These also return true or false, and basically you can say is the result X or whatever it is it missing or null, or is it logical or double or whatever it is. One of these things. These are all kind of is statements. You can put. So anyway, once you have a logical value, a true or false, we put it inside a conditional thing, and we go from there. Have I given you view quiz answers? I forget. Any of them? None of them. I've given you none. Okay, let's give you the first view quiz answer for today, which is the letter D. D as in dog. D as in dog is your first view quiz answer. So jot that down. I will give you the other view quiz answers later. D as in dog is your first view quiz answer. All right, so kind of the most important of these conditional statements is the if statement. Anything you put inside the if, that will be your condition. And the result of the condition has to be a true or false. And we want a length 1 logical value. And that value cannot be missing, right? It cannot be missing because the way the code works is if it's true, it executes the code. And if it's false, it doesn't execute the code associated with the if statement. And so if you have a missing value, whatever you do is taking a choice, right? So if you execute the code, then you're treating that missing as true, and that's not how it works, okay? And then if you have a missing value and you don't execute the code, then you're treating that missing value as false, and that's also not good. So you cannot have a missing thing because either executing or not executing the code is treating that missing value as either true or false. So if you have a missing thing and it's inside a condition, you are going to get an error. So this is a very common mistake, or very common error. I should not say mistake, but it's a very common error that code will produce is if you have a missing value inside an if statement, it's going to say missing value where true or false is needed, okay? So anytime you encounter that, that means something in there is missing. Okay, another very common mistake, or not mistake, very common error is that argument is of length 0. Inside the if statement, you cannot have a length 0 thing. Again, it doesn't know what to do, and it has to make a choice. And so if you get argument of length 0, that's also going to produce an error. Here is the in operator. In operator, it checks to see if some value is in the other vector, okay? And so we can say is 1 in the vector x, all right? And I want you to get in the habit of using in versus something like equals equals, okay? To check for equality to see if something is in the vector, right? Because if you did 1 equals equals x, that's going to be vectorized, and you're going to produce a vector, and it's going to say 1 is equal to 1, true, 1 is not equal to 3, false. So you're going to get a vector of true, false, right? But here, we want is it in x, and that's just going to produce 1 true value. And we say, hey, if 1 is in x, which is true, print hello, that's true, so it's going to execute print hello, and it outputs hello. Here I have a comparison. Is x greater than or equal to 2? That's going to produce false for the first value. It's going to produce true for the second value. So now I have this logical vector with false and true, and we don't actually want that in our if statement. But R will take it, and it's not going to error out. It just gives you a warning and says, okay, if, and it gets this vector false true, and it says, hey, you know what, you gave me two of these things. I'm just going to use the first one. Okay, warning, condition has length greater than 1. Only the first element will use, so it's going to take just the false. And so it says if false, well, if it's false, we're not going to execute the code in here, so it doesn't execute any code. Okay, same thing, I just flip it around, so now it's true, false. Now we have if now it's true, it's going to execute this code, but it also sees that it's length longer than 1, and so it gives us the same warning, that the length is longer than 1, only the first element is used. But because that first element is true, it does execute the code here. And that's what we get. Perhaps better than using this thing where we get true false is you just kind of wrap it inside the operator any. Are any of these things true, right? Are any of the values of x greater than or equal to 2? Well, yeah, that's true, okay? And so in this case, now we got if, and this thing is true, this statement is true, so it's going to execute that code, and it executes it, prints that out. Here, we have that error that we encounter, missing value where true false is needed, and what's going on, all right, so recall the subsetting lecture. If you have an atomic vector and you give it an index of something that doesn't exist in the vector, so right, x is the values 1, 2, 3, and we're saying what's the fifth element in x, okay? Fifth element in x will return x subset single square bracket 5 returns NA. So we're going to say, is this missing value greater than or equal to 2? Well, that we don't know, that's missing. And so now we get this error, right? We have a missing value, and we don't know what's going to happen. Okay, so that's very common error. Anytime you see this, it means whatever's inside this if statement, right? So it says error in if this, right? So you can look at this code, and you can say, hey, oh, what's going on here? There's a missing value here, and we got to fix whatever is producing this missing value. Here's another operation. Here I have x as the vector 1, 2, 3. And then I have this function. I say, which value in x is equal to 4? Okay. Well, which value in x is equal to 4? Well, none of the values in x are equal to 4. Okay. And so what it produces is a length 0 vector. It says none. I don't have any indexes to give you for values that equal to 4. And so here we're asking the question, okay, which element equals 4, and is that element the fourth element, right? Is the fourth element equal to 4 here? And this is a length 0, right? So we have an integer 0 comparing that to 4, so this will be a logical 0, and we get an error here, right? If this is argument of length 0, this is another error here. So again, you encounter something like this, you know whatever is in here is a length 0 or a null or something like that. Here we've got nested conditionals. So this is, I think, familiar. So you have an if statement, and if that statement is true, then execute this code. And if this if statement is false, then we go to the else, and then we have another check, and we say else, and then check this if statement. And if that's true, then execute this. And if that's also false, then go to the else, right? And you can have, as many else ifs as you need, okay? And it's just going to kind of check this, and if not, then go to the next, and if not, go to the next, and if not, go to the next, so on and so forth, okay? And so let's just kind of see how this works, right? So here I got x is 0. Okay, well first, x is 3. X is less than 0, that's false, so it goes to this. X greater than 0, that's true, so it's going to print positive, and then it's done. All right, so as soon as it encounters a true, it executes the associated lines of code, and then it quits out of the entire kind of if block here. Here I've got x is 0. This is false, so it doesn't execute. It goes to the next else statement, else if, right? X greater than 0, that's false, so it doesn't execute this. It goes to the else. There's no condition, so it prints this out. And there we go, print 0. Here I have x is 3, and here I say if x is greater than 0, print positive. Well, this is true, so it executes this code, and it prints out positive, and then it's done, okay? Once it hits a true statement, it kicks out of the entire kind of if conditions, right? Once it goes down this path, it's done. And this will only get looked at if this statement is false, right? So this else if x greater than 1, this will only get executed if x greater than 0 is false, okay? And so this statement will never get evaluated because there's no situation where x is greater than 1 and this thing is less than, this thing is false, right? X greater than 0 will never be false, and this will be true. So this line, bigger than 1, will never get executed according to this code. One thing to keep in mind is that the if statement is not vectorized, okay? And if you do want something that is vectorized, we have a function called ifelse, all right? And so this is something to keep in mind. Sometimes you write a function, and you want the function to be able to, like you have a vector and you want to run the function at every element in the vector, okay? Well, if your function uses an if statement, which is a very common thing, then that function is not going to be vectorized, all right? If you want to run that function on every element in a vector, then you have to kind of set it up inside of a loop. And you have to say, like, for each element in the vector, execute this function, right? And you do one element of the vector at a time. If you want something that is vectorized, where you can kind of put an entire vector into it, and it checks a conditional and it does it, then you got to use if-else, all right? And the way if-else works is it evaluates the condition for every element in that vector, and you're going to get, internally it thinks of this entire like vector of trues and falses. And then for everything that's true, it's going to execute this line of code, and for everything that's false, it executes the other line of code. So here, we can run if else x equal to 5. For everything where x is equal to 5, we're going to put yes. And for everything where x is not equal to 5, we insert no. Okay, and you can replace the yes or the no with some expression, but that's how this vectorized piece of code will work. And I've got an example of this later. Okay, let me go ahead and give you your second view quiz answer. Second view quiz answer is the letter C. C as in cat. C as in cat is our second view quiz answer. All right, let's take a look at loops. I think we're familiar with loops. We've probably seen some of these in Stats 20. But let's start off with the for loop, okay? And this is probably one of the most common things, and this is kind of one of the most common expressions that we see, for x in 1:10. And this part is, you could put in any kind of vector, all right? So very frequently we use an integer vector of like 1 through 10, 1 through 100, or whatever it is, okay? And then we execute this line of code for each element in that vector. So here we're going to cat x squared, okay? And then, in your homework I ask, what's the difference between cat and print? And cat basically outputs stuff to the screen, but doesn't actually return values or anything like that. And so here we're going to do, for the first element in x is 1, and we print cat 1 squared, or 1, to the screen. And then we go to the next value. X is 2, 2 squared is 4, and we cat that to the screen. Next element in x is 3, 3 squared is 9. We cat that to the screen, and so on and so forth, until we get to the end of the vector, which is 10, and we cat 100 to the screen. That vector doesn't have to be an integer vector. It can be any kind of vector. So here I have a list L. What is the length of L? The length of L is, it's a train with 3 cars in it. Okay? First car contains the integer vector 1, 2, 3. Second car contains the character vector A, B, C, D, E, F, G. And the third car contains the logical vector true, false. And we could say for each element in L, okay? So we're looking at basically each train car, all right? We're going to ask, what is the length of the element in there, right? So we're going into each train car and we're pulling out the object, all right? So we're going to say for y and L, okay, print the length of y. So it looks inside that first train car and says, how long is that object? 3. Then it goes to the next train car. How long is that object? Length is 7. Okay, third train car, how long is that object? Length 2. And so we print out 3, 7, and 2 onto the screen. And so you can do any vector. It doesn't have to be, we're most commonly probably accustomed to seeing integer vectors, but again, it could be any kind of vector here, right? Here's another vector, all right? So here's a vector of the first 5 alphabetical state names: Alabama, Alaska, Arizona, Arkansas, California, right? So R has a few built-in data sets. You can do library data sets, and inside data sets, one of the values is state names, and that's going to have the names of all 50 states. And so we can say, for each element in this vector, for state and state name, okay, state name 1 through 5, which is just this, we can say, okay, take the state, and it's going to be the string Alabama. And we're going to say, we're going to cat Alabama has, and we ask what's the number of characters in that value, 7, okay, 7 in Alabama, and we cat letters in its name, and we go through and we can say, all right, how many letters are in each of these things? California has 10 letters, etc., etc. Frequently, as you work through a loop, you need to store the results of your loop somewhere so you can use those results later. This is my recommendation, is that if you know how many iterations your loop is going to run, create a place to store the values of that size. So here, I've got results is a vector, and we're going to store 10 million results here, 10 to the 7. And so I create this thing in memory, length 10 million. And then we're going to sequence along. Sequence along the results will produce a vector starting at 1 of the appropriate length. Okay, so it's going to end at 10 million. And then so it's going to store in results position 1, 1 squared, position 2, 2 squared, position 3, 3 squared, all the way up to 10 million. And it stores those things. And I put that inside system time, and I say, how long did it take? And it went through 10 million things, operations, and it took less than 1 second, 0.64 seconds, okay? Compare that to this thing where I just say, hey, start off with a results vector that just has the number 0 in it, and then into position x, put in the value x squared. And this thing is a little bit slower. And the reason why is because R has to resize the vector every time it does, right? The first time it replaces it with a 1. Then it says, oh, you want to put into position 2 the value 4. And then it runs the loop again and goes, oh, into position 3, you want to put the value 9. And so it has to resize the vector every single time in memory, and that takes a little bit of time. And so it slows down, and it takes a little bit more than 4 times as long to do this, okay? Now, if you don't know how big your results is going to be, this might be the only way to do it, okay? So if you don't know how many iterations it's going to run, you might have to do it this way, and it's fine, but just know that it's a tiny bit slower. But again, if you don't know how many iterations your thing is going to run because it's like in a while loop, then this might be the only way to do it, okay? One thing you want to avoid, though, is copying the results every single time, okay? Now, again, sometimes this might be the only way to do it, but if you can avoid this, you don't want to do this, because each time here I start off with an empty vector, and then I say take the currently existing results, combine it with the new thing that I want to do, and store it into results, right? And then I'm going to repeat this, and I take the existing results, copy it, and combine it with a new element and store it back into results. And so we have to kind of redo this. And so this time I'm only going through 1 through 100,000, 10 to the 5, which is 1/100th of the amount of work. But you can see this took 13.6 seconds compared to 2.83 or 0.64. So this is much, much slower. And this is even only 1/100th. And if I tried to do the whole vector of 10 million, that would have kind of stalled my computer out. So this you kind of want to avoid if you can. Let's take a look at while loops. Okay, while loops will keep running until the condition is false, right? So basically, this is an if statement up here. It's a conditional statement, and it executes the code as long as this statement evaluates to true. And when it evaluates to false, then the while loop stops. So here I start off with I equal to 1, and it checks this condition. Is I less than or equal to 10? That's true, so then it executes this code. Into results position 1, store 1 squared. Okay, then increment 1, add 1 to I, and I becomes 2. Then it checks, is 2 less than or equal to 10? That's true. So then it executes the code. And what we end up getting is we end up getting the results vector. It has the values 1 through 100, okay, because it gets to 10 and it stores into position 10 here, okay. What's the value of I when this code finishes here? Is it 10 or is it 11? What is it? Okay. I takes on the value of 11 here, okay, because it gets to 10, okay, and it stores into position 10, 10 squared, and then it increments I to 11, okay, so I takes on the value 11, and then it executes, it goes back to the top of the while loop, okay, and then it says, is 11 less than or equal to 10? That is false, and so it kicks out, okay, and so it doesn't execute the lines of code. So I is the value 11, and then the while loop stops. Okay, repeat is similar, and it's kind of like a while true, right? And basically it's going to just keep repeating whatever's inside the loop until it encounters a break. If you don't have any kind of thing that says break inside your repeat loop, it's going to run forever, okay? And so here, we start off with I is 1. It does 1 squared, stores it into results I, increments I to 2, and then it keeps running until it encounters this thing. If I is greater than 10, then we exit out. So it gets to into I is 10, into position 10, store 10 squared, and we put in 100. Then it increments I to 11, and then it evaluates this. If 11 is greater than 10, that's true, then we break, right? So I here, it takes on the value 11 as well. We've seen this keyword break. There's another keyword next. So here's a question. What is this chunk of code going to output? We start off with I. We start off with this vector 1 through 10. So I takes on the value 1. And then it says if I mod 2 is equal to 0. I mod 2 equals 0 is checking if it's even, okay? So I mod 2, if I is 1, this is false, so it doesn't execute break, and it's going to cat 1 to the screen, okay? Reaches the end of the code block, so then it goes to the top, and it goes to the next iteration, all right? And so now I is the value 2. If I mod 2 is equal to 0, that's going to be true, then it breaks. All right, and then when it hits a break, it quits the loop. So all this is going to output to the screen is 1, okay? And if we ask what is the value of I, internally I is the number 2, okay? And that's when it quits. Okay, what about this? Instead of the word break, it's the exact same code. I've replaced the word break with next. Okay, I starts off with 1, it outputs 1, and then it goes to 2. 2 mod 2, this is true, so it hits next, okay? When it hits next, it goes back to the top of the loop. It ignores any kind of code that comes after next. So it's not going to cat 2 to the screen. Then it goes to 3. 3, this is false, so it doesn't execute the code inside, and it cats 3 to the screen. Then it goes to 4. This is true, it executes the next, it skips everything else. And so we end up getting only the odd numbers, 1, 3, 5, 7, 9 output to the screen. Internally, I does reach the value 10, and it just hits the next. And then it says, oh, there's nothing left, and it's done. So internally, I has the value 10. Okay. Again, as you review your notes, as you study and stuff, ask yourself these questions. Can I understand what this code is going to output without necessarily having to type the code into the computer? And if you need to type the code into the computer, do it. Okay, but you want to kind of be able, you want to develop that skill of being able to read code and understand what it's going to output. Okay, that's an important thing to develop. Okay, these functions, sequence along, and sequence length, are important because these produce integer vectors of the appropriate length. Because a lot of times we want to have that index available to us so we can kind of work with it. So rather than iterating through the actual list elements, we might create an integer vector. So we have list L, length 3, and we want to create a vector that's equal to 1, 2, 3, and then we can say, all right, into position X, position 1, extract out the first element of L, right? So we do L double bracket X, pull out the first element in L, give me the length, and store that. And so this is going to produce 3, 7, and 2, but it's working along that vector 1, 2, 3. Now, a very common idiom that you see is 1 colon length L, right? So you have some object L, and you say, all right, what's the length of that? And we want to go on a vector 1 through L. And if L is length 3, then this will produce the vector 1, 2, 3. And this is the same thing as doing just sequence along L. Sequence along L, we'll say, okay, well, L is length 3, and we're going to produce a vector 1, 2, 3. And that's also the same thing as doing sequence underscore length of length L. Length L is 3, so sequence underscore length of 3 is also going to produce a vector 1, 2, 3. So these all feel like they're the same. But this first one, which is probably one of the most simple things to do, I would recommend not using, because there is a key difference, and that is when you have a length 0 object, right? So here I'm creating a list, an empty list, and what is the length of L here? The length of L here is 0. And if you did 1 colon length L, this is going to produce a vector of 1, 0. And if you try to execute this in a for loop, this will produce an error. So if I say, okay, let's subset list L based on the index, okay, well, it's going to produce an error. It's going to say L double bracket 1, that doesn't exist, and we get this error, subscript out of bounds, okay? Because doing 1 colon list L, this doesn't work if you have a length 0 object, right? So instead, use something like sequence along. Okay? If you have an empty list and you do sequence along L, you get a 0 length vector. Okay? And if you do a for loop on a 0 length vector, it just says, well, there's nothing to execute, and it doesn't execute anything, and there's no error that gets produced. Okay? Sequence length also, similarly, when you ask what's the length of L, it's 0. Sequence length 0 produces a 0 length vector. Also, no problem there. Okay, let me give you your last view quiz answer. Letter E. E as in elephant. E as in elephant is your third view quiz answer for today. E. Okay, let's talk about vectorizing our code. Vectorizing our code helps kind of make our performance in R better, okay? You know, I love both R and Python, all right? And I feel like R gets a little bit of a bad reputation. People say like, oh, R is not useful or whatever. And I think that's unfair, because I think R is such a great tool, especially for data science, data exploration. The tools ggplot, I think, are really hard to beat, and the tidyverse we're going to cover a little bit later. Incredibly powerful stuff for exploring data. But I think one of the reasons why R does get a little bit of a bad reputation is because when you have for loops, it's slow, okay? And that's true, all right? A lot of your code can be sped up by vectorizing it, because when R does vectorized operations, it's very fast. But when you have a bunch of for loops, yeah, it's true. R is a little bit slower, okay? That said, if you try to optimize your code, you might end up breaking it, okay? And so it's better to have inefficient code that works than optimized, quote-unquote, optimized code that doesn't work, okay? But yeah, you know, as you're doing your homework, you might think like, oh man, this is not a great way to do it. And if you are able to if you have the time and energy to invest in optimizing your code, I think it's a worthwhile experiment, or a worthwhile endeavor to learn and develop that skill, to learn how to vectorize stuff. But anyway, let's cover a little bit of tips. We're going to run out of time. You're going to have to read some of these slides on your own time a little bit later. But let's take a look at some of this stuff here. Okay. So here's a situation where you might encounter, right? So here's a function, and it's a piecewise function. When x is less than 0, it's going to evaluate to negative x cubed. When x is between 0 and 1, it evaluates to x squared. When x is greater than 1, it evaluates to square root of x. And you might look at this and you say, hey, let's set this up. Let's set up a function with an if statement. If x is less than 0, the value is going to be negative x cubed. If x otherwise, meaning if x is greater than 0, and if x is less than 1, then it's x squared. And if that's not true, meaning x is greater than 1, then it's the square root of x, right? And I think this function makes sense. Return that value at the end. This makes sense. One problem, though, is that this is not vectorized. So if you try to give it a vector, what's it going to do? Okay? So here I create this vector, and I say, hey, I want to evaluate this function for everything between -2 and +2, all right? And I create this sequence by 0.01, so I go -2, -1.99, -1.98, all the way to 0, 0.01, 0.02, 0.03, and then up to 2, okay? And what it's going to do, all right, and I say, hey, do f on x, store those results into plot values, and what do I end up getting? I end up just getting negative x cubed, all right? And what happened is, well, it took that vector and it said, okay, my first element is -2. If x is less than 0, that's true. Evaluate negative x cubed. So it takes the entire vector now, it cubes it, all right? And then it stores that entire vector, right? And so now we just have that entire vector, negative x cubed. Now it gives us this warning. It says condition is length greater than 1, okay? And that's because it's got this length, 401 vector. And just uses that first value, which is false, or which is true, and then -2, and it evaluates that, okay? So this is not what we want. What we want is we want to evaluate it. And so we have to, if this is our function, we have to put it inside a for loop, okay? And so inside the for loop, I say, take each element in x, okay, subset it to that value, put it inside the function, and store it into position I into this vector plot values, okay? So we can do that, and then, so it starts off with -2, evaluates it, and we get 8. Then it goes to -1.99, it evaluates it, and it gets the next value, -1.98, evaluates it and gets the next value, and it does this individually for each value, and then when it gets to 0.01, it goes through the condition, evaluates it, and now it does that squared, and so on and so forth, and this is what we get, okay? So this will work, but we had to put it inside a for loop and do each value individually because it's not vectorized. But this is a little bit slower, so what if we wanted to vectorize our code? Okay? If we want to vectorize our code, we can use this if-else. Okay, if-else is vectorized. Okay, and I have to use a nested if-else. All right, so I have this condition: if-else, if x is less than or equal to 0, then this is what it's going to evaluate to: negative x cubed. All right, and if that's not true, then we run another condition. We have another if-else. Okay. And we're going to say, basically, if that's not true, then check if x is less than 1. And if that is true, then do x squared. And if that's not true, then do square root of x. This is vectorized. And this will evaluate, and I can kind of just make it into a one-line function. This is f2. And here, I can just take the entire vector, -2 to 2, and I can just plug that into the function x. This is vectorized. Take those values, plot values 2, and now I get the entire result. I didn't have to put it in a for loop. It is vectorized, and it gives us all of our values. Okay? But what happened here? I get this warning: square root of x, nans produced. Okay? And you go, I don't have any missing values. None of my values are nans. Okay? Well, the way if-else works is it evaluates both the true and false for all the values in x. Okay, so it takes -2 to +2, and it evaluates negative x cubed. It takes -2 plus 2, and it evaluates all of these things, x squared and the square root of x. So it evaluates all of these things, all of the outputs of if-else for all of the values inside x. Okay, and then what it does is it takes the results and then it says, okay, wherever it's true, then we're going to find those values and put them in, right? So it evaluates negative x cubed for the entire vector. It evaluates x squared for the entire vector. It evaluates square root of x for the entire vector. And then it just selects the values for which it's true. And so in that case, even though it doesn't actually output, okay, it did evaluate square root of x for like -2 and -1.99, and then anytime you put in a square root of a negative number, you're going to get a missing thing, okay? And that's why you're getting this warning, even though in the output there's actually no nans, okay? No knotted numbers there, okay? Go through these notes on your own. This is for like dealing with matrices, and if you have to do like column sums and row sums, there's nice little built-in functions that do these operations very quickly. All right, we'll end here for today. Have a great rest of your day, and we will see you Friday.